Well, Magda, thank you very much for that introduction. I would like to kick off, as Magda has indicated, I'd like to kick off the International Year of Physics 1 year early with my lecture here tonight on the 19th century World Wide Web. And in particular, I wanted to highlight the role of one of the most eccentric physicists in the history of legions of eccentric physicists, Oliver Heaviside, because his name does not have the prominence I think it deserves, considering the significance of his work. I should also start this lecture on a personal note. For the last 15 years I've been giving July lectures to the general public, but this year is special for me because on Tuesday of last week I was promoted to a full professor of physics here in the School of Physics at the University of Melbourne. Today is my first official event at the university in my new capacity, and it's to this audience, so thank you for coming. Okay, so I wanted to just give a quick history of the personalities involved in the development of the electrical technology that led to the World Wide Web. And really all this got started with Michael Faraday, whose work was then drawn on heavily by James Maxwell, who was then looked at by Lorentz, who finally was set right by this guy. But this guy I can't mention because this is about not about 1905, this is about what happened up before Einstein here had his marvellous ideas. So this lecture will stop before I can talk about what's going on in his mind. So let me just give you a quick outline of what I'm going to be about. I'm sorry, it's a little warm up here. I wanted to divide my lecture tonight into three parts. Part one, I wanted to talk about a fast history of electromagnetism. That should take us up until about breakfast time tomorrow morning. And I wanted to highlight where Oliver Heaviside fitted into this history of electromagnetism. Then I wanted to get on to the development of the electric telegraph, because so much of the physics of the electric telegraph opened the door into 20th century physics, and in particular the emergence of Einstein's relativity. Some very surprising aspects of the electric telegraph technology, in particular the contribution of Oliver Heaviside, almost delivered Einstein's theory of relativity some 10 years before Einstein. Then in the third part of the lecture, which will probably finish around dinner time tomorrow, I wanted to describe Maxwell's equations. Now, it's always said that if ever you're doing a popular book or a popular lecture and you put an equation on the screen, most of the audience will fall asleep and they certainly won't buy the book. But I can't avoid it because the equations are just so nice, and Heaviside's contribution was just so important in straightening these equations out that I have to show them to you. And I really, although everything we know about electromagnetism is summed up in what's now called the Maxwell equations, they really should be called the Heaviside equations, so I hope I'll persuade you. Okay, so let's begin with part one, the history of electromagnetism in about 10 minutes. First of all, the field got started about 3,000 years ago when natural magnets were discovered in the district of Magnesia in Greece, home of very good soccer players apparently. And here is a piece of natural magnet. You can see this guy discovering one in the field when his sheep prodding implement there sticks to a rock through the magnetic force. So this is a piece of lodestone. It's not a very strong magnet, and I think it's been used in too many lecture demos, but nevertheless it is enough to disturb compasses and so forth. So this was the first discovery of a force of nature other than gravity, which of course everyone already knew about. And nothing much happened for the next couple of thousand years until it was discovered that the Earth in fact acted as a giant lodestone. And William Gilbert, who was the personal doctor of Queen Elizabeth I, was the one who described the Earth as a giant magnet, and he introduced the words electric force and electricity and demonstrated that you could make a model of the Earth with a spherical lodestone and track compasses over it. And I guess he explained that, oh, Your Majesty, you have a cold, okay, take 2 aspirins, call me in the morning, but let me tell you about my latest magnetism experiments. And I wonder if the Queen Elizabeth II's doctor says, Your Majesty, you've got a cold, take 2 aspirins, call me in the morning, and let me tell you about our search for the Higgs boson, or something like that. I'm sure he does. But then it moved on. Slowly, electricity began to be studied more and more. Ørsted discovered that an electric current would actually make an electric field, a pretty crucial discovery. And Ampere, French guy, put all that electric currents and magnetic fields onto a firm footing. And Faraday then discovered what is now the basis of a $1 trillion industry, namely how to make electricity by rotating coils of wire inside magnetic fields, Faraday's law of induction. This was also discovered simultaneously by an American called Joseph Henry, but Faraday published it first, Henry didn't, so it's Faraday's law of induction, not Henry's. That's the publish or perish phenomenon. Then Maxwell studied all of these disparate phenomena in electricity over here, magnetism over there, put it all together into his 40 compact equations, which were the first Maxwell equations. And I'll show you why the Maxwell equations were so complicated, and there were so many of them, shortly. Then Lorentz came along and said, look, we can understand all of this electromagnetism in terms of moving charged particles. He didn't quite use that language, but shortly thereafter, the nature of the moving particle was discovered by J.J. Thomson, who discovered the electron in 1899, which was the basis behind electricity and magnetism. And those of you who were around in 1999 will recall we had 4 July lectures on the theme of the 100th birthday of the electron. And then this last guy, who I'm not allowed to mention in tonight's lecture, came along and swept everything away, turned physics completely upside down, drawing startling new conclusions from this physics of electromagnetism, and I'm going to try and show you tonight where some of those ideas came from. And this guy doesn't get a mention in this official history of electromagnetism, for this is Oliver Heaviside. His life spanned this era, where electromagnetism went from a sort of obscure hobby into a very solid theory of the way the universe works, giving fundamental insights into light, time, matter, everything. And yet his name scarcely rates a mention, and it's no wonder he's looking a little bit unhappy in this photo. So I want to try and highlight what he did. So let me just do some critical electromagnetism experiments for you, in case you haven't seen any of this. Because there's a little bit of a problem with electromagnetism in terms of classical physics, and I want to try and show you what that is. There isn't really a problem, because Einstein explained it away, but let me just show you some crucial experiments. Here I've got 2 lumps of matter inside this big flask here, and these are being sprayed with a conductive metal paint, and they're connected by 2 little wires to a high voltage power supply. So what I can do is charge up these 2 little balls, so I can drag some of the electrons off them. And when I do that, they repel each other. So this is the first result of electromagnetism, that if you charge something up, typically by drawing electrons off or putting them on, you get the result that like charges repel each other. I can draw the charge off again, and they go back to not repelling each other. And so this is the fundamental result in electromagnetism, that you get a force between charged particles that depends on how much charge you put on them, how much electric charge you put on, how far apart they are. Then the next critical result in electromagnetism is the idea that a moving charged particle experiences a magnetic force. So here I have a bar magnet, and here I have some moving charged particles, namely a stream of electrons that have been ripped out of a hot filament and accelerated up to a reasonable speed, and then they then streak along this green stuff and scintillate, so you can see them moving. So there's lots of electrons moving towards the roof. If I now come in with a magnet from behind, you can see that the path of the electrons becomes deflected. And it's a very strange force, the magnetic force. In fact, if I reverse the direction, so that was with the blue end of the magnet pointing towards you, now with the red end, you can see that the electrons deflect in the other direction. I'm not saying anything, let me check. Oh, it's working. Okay, good. Now, this is very odd because what's happening here is that we've got electrons travelling in the vertical direction. So I've got an arrow here to show you the direction of the electrons. And I've got a magnetic field which is sticking out at the end of the magnet pointing in the horizontal direction. And this then ends up with a force at right angles to both of those directions. Very complicated situation here. It's not like a very straightforward thing like this where they just repel each other. You've got these complex vectors, as they're called, or arrows that give the direction of everything that's going on. And it's often convenient to use your right hand to say that the force on a charged particle is given by the direction of its velocity times the direction of the magnetic field in this sort of scenario. So you can always figure out which way around it goes, but you have to flip your thumb over if they're negatively charged particles. And quite often when I'm driving, actually, I notice people doing things like this out the windows of their cars. It's like, the Earth's magnetic field, moving charged particles in the car. Yes, there's a sideways force here. At least I hope that's what they're doing. Anyway, so this is very odd. It's even more odd in that the force, so here's the moving charged particle, there's the magnetic field, and in this case the force will be into the screen if that's a positively charged particle. It's very curious, this force, because it depends on the speed of the charged particle. You have to plug in the speed. The force goes away if the particle isn't moving. Now that's a serious problem because what speed do I plug in for this speed here? These electrons, of course, are streaming towards the roof, but this lecture theatre is presently plunging around the sun at a speed of about 30 kilometres a second, and at this time of night it's, that way. And that's a pretty high speed, so there should be enormous magnetic forces on these electrons, even if I turned off the accelerating voltage and just let them sit there, but no such force is ever observed. So this is a bit of a problem, that having this velocity-dependent force here. Now, when the magnitude of the force was first calculated by J.J. Thomson in 1881, he got it wrong. He said the force was equal to QV times B, and he had a factor of a half out the front there. Then Heaviside, Oliver Heaviside, the hero of tonight's lecture, he came along in 1889 and said this is wrong. He recalculated it and said it's QV cross B here. He got it right. And for some reason this force is not called then the Heaviside force after the guy who got it right the first time, because this guy Lorentz came along in 1892 and took Heaviside's result. He took the Coulomb force law, which had been around for a long time, and he just wrote them down together. So these electrons are experiencing an electric force from the accelerating voltage in the vacuum tube here. That's the first part, QE, which is the same as this force up here. And he added and said, well, if there's any magnets around, we better include the force that the magnet is exerting. And he called that, or other people then called that the Lorentz force. But it really should be called the Heaviside Coulomb force in my view. Right, so with all that, that was the end of the history of electromagnetism in 10 minutes for you. Now I want to look at how this, these ideas gave birth to the electric telegraph. And in particular, some of the amazing technical accomplishments of the electric telegraph, which are largely forgotten today. Samuel Morse invented Morse code and then strung a wire from Washington to Baltimore. I think it's only a few hundred kilometres, and this was the first demonstration that you could transmit information down a long wire by means of pulses of electric charge, pulses of voltage, if you like, switching things on and off. And this was a great idea. It revolutionised communications, which had to be done by ponies or something before this time. It wasn't very convenient, it took a long time. So cables started to be strung long distance, and the first cable went across the English Channel in 1850. It didn't last very long till the seawater wrecked it. But soon new cables were strung, and England and the continent were connected. And even right down here in 1854, only 20 years after Melbourne was founded, the first cable was laid down to Williamstown from the centre of Melbourne for communication with the docks. And 4 years after that, an ambitious attempt was made to string a cable all the way across the Atlantic in 1858, and that cable only lasted for a few months before it failed. The technology had been pushed too far. But in 1859, a cable was strung from Cape Otway across to Tasmania, an extraordinarily early result, considering how early our colony, how young our colony was at that time. But that cable only lasted for 3 weeks before it too failed, and it was later grappled up out of the bottom of Bass Strait and relayed across the Timor, across the Torres Strait, where it failed again after a few weeks. So then they gave up and left it there at the bottom of the sea. Then in 1862, Stuart crossed the continent for the first time, and the South Australians, as entrepreneurial as ever, said, we know almost nothing about the interior of our continent, but we know that there's a telegraph cable coming down to Indonesia. Let's string a telegraph wire across the unknown interior of our continent. After all, it's only 3,200 kilometres of trackless desert with no water. No one knows what's out there apart from the narrow strip that Stuart walked down. And surprisingly, after only a few months of debate, and spurred on by the fact that the Queenslanders were trying to get a cable across the top end and then down the east coast, which would have been the sensible thing to do, were in an advanced state of planning. They rushed into it and laid the cable across the centre of Australia. Many people died of thirst. The Indigenous people weren't too happy about this, but finally in 1872 the overland telegraph was connected with the undersea cable from Java, and Australia was online for the first time. And this revolutionised communications between Melbourne and Sydney and the other places in Australia and Britain and Europe, because you could send messages in only a few hours, whereas previously everything was weeks and weeks old because it all had to come by ship. Then in the next few years, further undersea cables connected Australia to the outside world, and I'm going to return to this one here, the all-red route, because that was the pinnacle of telegraph technology. And I think the last use of the old overland telegraph across the middle of Australia was during World War II, when it reported the bombing of Darwin when the Japanese came down. So again, this red bracket illustrates the life of Oliver Heaviside, which spanned all these astounding technical developments of the telegraph. So let's look at Heaviside's life, because it's a very unusual life even by today's standards. Born in 1850 to a lower class family, as it was in those days. This was a serious handicap with getting on in society, and it often meant that his ideas and his work were not taken seriously because of his social class background. He decided that by the age of 16 he'd had enough of schooling, and so he left and then embarked on a course of self-study and taught himself Morse code. He then used the influence of his uncle, Sir Charles Wheatstone, of Wheatstone Bridge fame, and I see there are a few people with grey hair in the audience who know what a Wheatstone Bridge is, probably. Yeah, good, a few younger people as well. And Sir Charles Wheatstone got him a job as a telegraph operator because he knew Morse code. So he stuck that out, and then on the fateful day in 1873, he went into his local library and he found lying on the table there a copy of Maxwell's treatise on electromagnetism with the 40 equations in it that I mentioned before. And Heaviside reported in his diary, "I saw that it was greater and greatest, with prodigious possibilities in its power." And that's an extraordinary thing for a young lad who had pretty much no formal education to say. And it had such a powerful effect on him, this book, that the year later he left his job at the age of 24 and never worked again. Because he devoted the rest of his life to exploring the consequences of the Maxwell equations. He rapidly made progress. He derived the field of a moving charge. This is a very difficult result, and it's right at the very heart of Einstein's relativity, as I'll explain later on. Already in 1881, he had relativity, but he didn't know what he had. He then rewrote the Maxwell equations from the 40 complicated equations that Maxwell had written down to 4 simple equations involving a new concept called the vector, which Heaviside invented. He then did a whole lot of mathematics, which was a bit dodgy, but gave the right results, so what do we care? Only the mathematicians were at all worried. He then invented his circuit for high-fidelity telegraphy to avoid problems of distorted signals, and for this accomplishment he became elected to the Royal Society, became a Fellow of the Royal Society. He then investigated the new quantum mechanics and demonstrated that atoms could not possibly exist. He proved that mathematically no atoms existed because of the fact that a moving charge radiates energy away, which would cause all atoms to collapse. And in this, Heaviside met his limits because this was the advent of quantum mechanics and he never got into it. The world eventually left him behind. But he had still some creativity left. In 1902, he introduced the idea of the Heaviside layer, the layer of ionisation in the upper atmosphere that allows radio signals to be bounced around the world. Unfortunately, after 1902, his mental state began to deteriorate somewhat. I mean, it was never crash hot from day one, it has to be said. But he became a recluse. Well, he was always a recluse, actually, but he became a real recluse then. And sitting at home, doing equations, doing maths all the time, year after year in isolation, he awarded himself the title WORM, Oliver Heaviside WORM. And when people asked what it stood for, he said it didn't stand for anything. In 1922, he was awarded the Faraday Medal by the Institute of Electrical Engineers, I think it was. And when he received the letter notifying him of this award, he stood back and said, "Ha, if that's the highest medal you've got to award, I suppose there's no Newton medal then, is there?" Because Newton presumably was better than Faraday. And then finally he passed away in 1925 at the ripe old age of 75, and for the first time the 20th century intruded on his life when he got put in a motor vehicle and taken to hospital. So 25 years into the new century was the first time he went in a motorised vehicle. So what's behind this eccentric man? He lived with his parents until they died, and then he lived on alone in their house. He shunned all contacts with his fellow scientists. If you look in his diary and his letters, there are hundreds of invitations to speak at conferences, to come to dinners, to banquets. He declined them all. Whenever he was given an award, it was always done on his terms. I won't come, just send it to me. He also felt the cold. His annual gas bill completely exceeded the value of the stipend he received from the Royal Society in recognition of his accomplishments, and some generous fellow scientists picked up the bill. I don't know what he used for food, but he used all his money for buying gas to try and keep warm. As I said, he had this very strong instinct for getting the right answer in electrical problems, so he invented all this new maths, which the mathematicians didn't like, and it even made them even more irritated when the new maths kept giving the right answer. And there's a legend that towards the end of his life, he threw all the furniture out of his house and replaced it with blocks of granite. It's a more austere environment for thinking about electrical problems, but that may be an urban legend. I don't know, I haven't seen much independent correlation of that. But he also loved cycling, and there was a fellow scientist who was the only person he would allow to come near him, and they would often go cycling together. Now, he published his work in summarised his work in these two books, which he called his Electrical Papers, Volume 1 and 2. Very hard going, even today. And there are rumours that he published a third volume, but this has never been found. Or maybe it hasn't been found. I'll get back to that towards the end of the lecture. He also published 3 books on his electromagnetic theory, volumes 1, 2 and 3, which are still worth reading even today. A lot of his very high-powered results were published in high-quality journals like the Philosophy magazine, but by far the majority of his work, no matter how technical, how difficult, was published in The Electrician, which was nothing more than a weekly trade journal. So it's hard to imagine what the readers of this journal would make of Heaviside's very dense papers with the complicated maths in them. So that would be the equivalent of me publishing my latest experiments in Silicon Chip magazine. So I'd really like to get an article in that journal actually, but so far I've never succeeded. Okay, so that's the history of electromagnetism and the history of Oliver. Let me now turn to the technical aspects of